Greetings to everyone. Thank you to the organizers for this opportunity to make the presentation online. I am Yuvaraj, research scholar from Indian Institute of Technology, Madras. In today's presentation, I will talk about the role of pore network parameters to link physical structure and transport properties in ternary binders involving auminosilicate-limestone combinations. This is the brief outline of my presentation, where I will introduce the context of the presentation in terms of opportunities and challenges associated with limestone addition, talk about the focus of the presentation, introduce the research matrix, and the results pertaining to role of limestone with respect to phase assemblage, physical structure development, linking pore network parameters and transport properties, perspectives on physical structure development, which will be followed by summary and conclusion. As we understand, limestone addition is one of the promising measures to lower environmental impact, and it is also expected to rise as per CSI report from nearly 8% as part of cementitious material to 18% over the next few decades. The limited availability of fly ash and slag is expected to be balanced by the increased use of limestone and calcined clay in near future. Another major context for limestone addition is the extremely low emission factor associated with the material in comparison with most of the alternate clinkers as well as alternate supplementary cementitious material. This makes it one of the viable cement substitutes to be used directly at the source for the cement production without much transportation that is involved in the material. And this is also available in the quantum that is meant to be used for the cement production to meet the demand in growing economies like the cement consumption in India, which is expected to grow fourfold over the next few decades. And the less energy and emission intensive, being a less energy and emission intensive material makes it adaptable as a general purpose binder in most of the blended cements as an additional component. The shift from binary and ternary systems is primarily due to the difference in the reaction chemistry and the phase assemblage. So when you replace some amount of clinker with the aluminosilicate-based SCM, the pozzolanic reaction, which leads to formation of pozzolanic CSH with low calcium sulfur ratio, leads to improved space filling and better post-structure development. When you replace additional amount of clinker with the limestone, there is a multitude of reaction that comes in. There is acceleration of clinker reaction, stabilization of wettingite, increase in the amount of carboaluminate phases. You have a combination of all these reactions contributing to the post-structure development in a composite binder. When we try to understand the impact of this multitude of reaction which is happening in ternary binders, the differences, the contributions are very limited in terms of its impact on compressive strength. You can see both binary and ternary systems nearly having a similar strength development in both the cases with fly ash and calcined clay based combinations. Even up to 20% limestone, the strength differences are quite limited. However, when we look at the impact on transport characteristics such as chloride penetrability or moisture ingress, the impact of dilution due to limestone addition is quite clearly visible. Whereas in the case of calcined clay, the ability of calcined clay to mask for the dilution impact and influence and transport properties is also quite clearly visible. In this context, it's necessary to streamline information and find ways to explain the differences which is brought out on these big areas by using a generic physical structure parameter in terms of porosity, pore structure, pore sizes, or pore connectivity. So it's necessary to acknowledge that there is major difference in the durability parameter rather than concrete compressive strength when we look at ternary binders. The focus of presentation is to look at the role of limestone in ternary binders, look at the influence of limestone dosage on physical structure development, role of pore network parameters to explain transport properties in composite binders, and to synthesize information on how physical structure develop in these cement composites. Mainly, the discussion would try to argue for the interaction between clinker and SCM by means of pozzolanic reaction and interaction between SCM and calcite particles from limestone in terms of carboaluminate formation. How these two interactions can complement or balance each other in the ternary systems. The research matrix include plain Portland cement, replaced with 5 different types of aluminosilicates, which includes calcined clay, 3 types of fly ashes, slag, and limestone, where limestone dosages are varied from nearly 10 to 20%. The studies were done both on cement paste and concrete systems with the following water binder ratio. In terms of phase assemblage, when you look at the impact of limestone, there is a potential to form about 5 to 25% carbonaceous phases in these systems, depending on the choice of SCM. You have calcined clay, slag, or fly ashes with reactive alumina. There is a higher amount of carbonaceous phases that is formed. Merely by increasing limestone dosage from 10 to 20%, 15%, or even further to 20%, you don't necessarily increase the amount of carbonaceous phases, which means it is necessary to understand the impact of this hydration products by increasing the amount of limestone substitute, as the hydration products are not necessarily improved with increasing amount of limestone at the expense of mineral admixture. So now, is it beneficial to have these hydration products at the expense of pozzolanic CSH? And what is the role of these alterations on the pore structure development? We try to address this using formation factor approach, which gives an indication of both porosity and pore connectivity by taking relative conductivity of the pore solution and the bulk conductivity of the system. These are some of the trends with fly ash limestone combination, where you can see the ternary binders having higher formation factor at early ages, and high volume fly ash shifts from the lowest value at the initial ages to highest value at about 400 days. When you move to systems which has higher amount of reactive alumina and carboaluminate formation, you can see a major shift in the initial few days, even up to 14 days, post which it follows similar kinetics of formation factor development like binary systems. The slags continue to evolve rapidly between 3 to 7 days, and calcined clay evolves much more rapidly between 1 to 3 days, where there is a major rise in formation factor for both binary as well as ternary systems. Because formation factor has direct implications on porosity and pore structure, we try to look at the implications of this parameter on the transport properties in concrete systems. When we looked at it, you can see the formation factor could explain both chloride transport in saturated concrete as well as moisture transport in an unsaturated concrete system by capillary absorption, which shows with all the intricacies that is present in concrete due to binder chemistry, mixture proportioning, formation factor in this is indicative of the physical structure that is present in the concrete system. We wanted to further decouple the information in terms of porosity and pore connectivity, where we took this factor beta and converted it into electrical tortuosity form that is presented earlier in literature, and try to adopt tortuosity based relationships to explain diffusivity characteristics. And these are the trends where you can see all the concrete systems fall in line with the theoretical lines of porosity of nearly 10 to 15%, which is expected to be present in the concrete systems. This shows that tortuosity could explain chloride transport under a generalized framework where it could account for both porosity as well as pore connectivity. The role of porosity reduction by fine-tuning mixture proportioning in concrete, as well as impact of reactivity of the material to positively improve pore connectivity, can be quite well captured using this from the set of results. You can see all the calcined clay systems have very low diffusivity, mainly because of the higher tortuosity factor, which is brought out by defined pore structure, which is developed in the calcined clay-based binders. In order to look at the impact of pore sizes on the formation factor development, we try to plot critical pore diameter versus pore sizes. What we identified was, in the early ages when the critical pore diameters are above 100 nanometers, also there is a minor increase in the formation factor, which shows the porous hydration products spread to reduce the interparticle space, where there is still a lot of high interconnected porosities that is present. Post the sizes reach a critical range of 10 to 30 nanometers, there is a major increase in the formation factor both for cement paste as well as concrete systems. This shows at the critical size range, there is significant depopulation of the capillary porosity, which makes the pore network highly tortuous. We categorize this as the densification regime, wherein when we try to process some of the result, we identified that once the critical pore size reach the size range of 10 to 30 nanometers, there is only reduction in the volume corresponding to critical pore size rather than shift in the pore sizes. when we try to understand whether it's the pozzolanic CSH or the formation of carboaluminates that lead to filling of pores corresponding to the critical pore size, we try to estimate saturation index for the range of different hydration products based on pore solutions that were assessed on these binders. And the saturation index corresponding to the CSH phase falls more or less in line with the theoretical size ranges corresponding to 10 to 30 nanometers, which shows that it is the formation of the pozzolanic CSH that is dominantly contributing to the densification at the later ages. Though there is major contribution of the carboaluminate phases to the reduction of the capillary pore space at the early ages due to high amount of carboaluminate phases that are formed in the ternary systems. By this way, we are able to synthesize a phenomenological framework to explain the densification process, where saturation in pore solution leading to hydration formation in the critical size ranges, causing densification of the pore structure, which leads to an increase in formation factor that controls transport property, were quite well linked up between by linking the processes at the different scales. To summarize, there is limited difference in concrete strength due to limestone addition up to 15%. The dilution impact is dominantly visible only in fly ash limestone combinations. The choice of SCM has a dominant control on the carboaluminate phases rather than limestone replacement level. It is necessary to supplement the carboaluminate phases with pozzolanic CSH for densification to occur at later ages. For both formation factor and tortuosity parameter could explain transport behavior in the composite binders. It is seen that the reactivity of the SCM primarily governs the kinetics of the physical structure development, and based on the trends of formation factor versus pore size, we identify a twofold structure development mechanism where there is initial convergence of hydrates in the capillary pore space to a critical size range. Once the critical size range is reached, there is densification of the physical space in the microstructure. With this, I would like to thank the Concrete Research Group at IIT Madras and the funding source for their support. Thank you. I will look forward to your questions.